Welcome to Unit 2.7 Electrochemistry, and in this video we're going to look at points 1, 2 and 3 on the specification. So just to briefly introduce you to this topic, we're going to be looking at a process called electrolysis. And essentially that process involves splitting up or breaking down compounds using electricity. If we look at that word electrolysis and we split it into two parts, electro and lysis. Let's look at the end of it first of all, this part lysis, and you might want to write this on the front cover of your booklet. You may have come across this term in biology. In biology it's the disintegration of a cell if your cell wall or your cell membrane ruptures. But we're not talking about biology here, we're talking about chemistry, and essentially this little suffix, if this appears at the end of a word, it essentially means to break down or to separate. So lysis means to break down or to separate. And then what do you think electro refers to? It refers to the fact that we're using electricity. So a very simplified definition of what electrolysis is, it's to break down or to separate using electricity. So keep that at the back of your mind, that we're splitting up things, we're separating things, we're breaking them down, and we're doing that using electricity. Over on page 2 we start with a couple of reminders of terms that you would have met in year 11. So first of all, we remind ourselves that cations are positively charged ions. So cations are positively charged ions. Sometimes we remember that by thinking of the T as a positive sign in the middle of cation. Then we have got a reminder of the term anion, and an anion is a negatively charged ion. Anions are negatively charged, and sometimes we remember that by thinking of that N in anion meaning negative, N for negative. So it's really important that you keep these definitions in mind with this topic. So cations are your positively charged ions, anions are your negatively charged ions. Then we're going to move on to some new definitions that you haven't met before. So remember that this word electrolysis essentially means breaking up or separating something using electricity. Now that wouldn't get you the marks in an exam, you do have to come up with an exact definition, but it's good to keep that at the back of your mind. We're splitting things up, we're separating compounds using electricity. One example of a compound that we might use electrolysis on is sodium bromide. So sodium bromide is an ionic compound. It's made up of a metal and a non-metal, and that's what we're going to be looking at in this topic, the breaking up of ionic compounds. It has to be molten, but we'll come back to that in a second. But essentially we're breaking it up into the individual elements. So if I was to break up sodium bromide, what would I get? I would get sodium and I would get bromine. So it's using electricity to split up a compound such as sodium bromide into its individual elements, sodium and bromine. Again, we'll look at more examples in a second, but that's just to give you a rough idea of what is happening. So here's your definitions, and you need to learn these. These can come up all the time, particularly electrolysis and electrolyte. So let's have a look at these definitions now. So the definition first of all of electrolysis, we've already talked about how it's separating compounds using electricity, but that wouldn't quite get you the mark. What you have to say is that it's the decomposition. Decomposition just means to break down. Again, you may have come across that term in biology. If something decomposes, it's breaking down. So it's the decomposition of a liquid electrolyte. We'll come to that term in a second, but essentially that's just what we are breaking up, and we're using a direct current of electricity. So it's the decomposition of a liquid electrolyte using a direct current of electricity, and you must learn that word for word. So electrolysis is the term for the process that is taking place here. So electrolysis is the process. We then come to this definition, electrolyte. An electrolyte is essentially a liquid or solution that we are doing electrolysis on. So it's the compound which has become a liquid, that we are doing electrolysis on. So the definition of it is the liquid or solution that conducts electricity. It's important that it is a conductor of electricity, otherwise this doesn't work, and is decomposed by it. So essentially it's the liquid or solution that we are breaking up. So again, learn that definition really well. The liquid or solution that conducts electricity and is decomposed by it. Essentially, it is the solution or liquid that we're doing electrolysis on, and you can see that labelled in your diagram here. The next definition is electrodes. And essentially the electrodes are the place where electrolysis happen. If you see in your diagram here, the cathode and the anodes, they are both electrodes. The electrodes also keep electricity flowing through our circuit here, and it's where our cations and anions are attracted to. But again, we'll come back to that. It's important just that you know a definition of electrodes and what they are normally made out of. So we say that they are inert rods. Essentially that just means unreactive, or chemically inactive, but unreactive is fine. So they're inert rods that are used to conduct electricity under unreactive. Essentially that's where your definition finishes, and then it just goes on to tell you what they're normally made out of. They're normally made out of graphite or another unreactive material like platinum. Graphite is more commonly used because it is cheaper than platinum, but platinum works all the same. Essentially what we need is something that is able to conduct electricity. So it must be able to conduct electricity. And if you wanted to even put a star beside graphite and put a star down here as well, it says graphite is often used for electrodes as it conducts electricity and is unreactive. So graphite is quite unreactive. So please make sure that you highlight that, because sometimes you're asked that in the exam. And why is graphite used as electrodes? And you're saying because it conducts electricity and is unreactive. Yes, it's cheaper than platinum, but don't say that as a reason why it's used as electrodes, because really you're just saying the reason why it's used over platinum. So yes, it is cheaper. If you were asked why is platinum or why is graphite used in preference to platinum, you would say because it is cheaper. But if you're asked why is graphite used as an electrode, you would say because it conducts electricity and is unreactive. That's a really common exam question. So electrodes are normally made out of graphite or platinum because they conduct electricity and are unreactive. So those are the rods that we put into our liquid or solution to conduct electricity through it, and that's actually where the electrolysis happens. So you'll notice from our diagram that we have two electrodes. We have something called an anode and an electrode called a cathode. They will both be made out of the same material when electricity is not flowing through the circuit. Essentially they're the same. They are both made out of graphite or of platinum. But when electricity is flowing through the circuit, one of our electrodes will be positive and one of our electrodes will be negative. And this is where it starts to get a little bit confusing, because up at the top of the page we said that anions are negatively charged ions. So you might expect the anode to be a negative electrode, but actually it's the positive electrode. I'm going to keep it in purple because I put my highlighted my anions in purple above. So the anode is the positive electrode, and that might seem totally confusing to you because anions are negatively charged. But have a think about why do you think that the positive electrode is called an anode? Why is the anode positive? Well, we're going to see that it's because anions are attracted to it. So if anions are negatively charged, remember, opposite charges attract. So the negatively charged anions are going to be attracted to the positively charged electrode. Again, we'll come back to that in a second. I know that's a bit confusing, but you've got to learn that off. You've got to get that right in your head at the start of the topic before we even go into the ins and outs of what's happening here. Because if you start to get confused about this, then you'll find the topic much more difficult. Therefore, the cathode then, which electrode is it? It's the negative electrode. And again, that seems confusing because cations are positive, but it's because the positive cations are attracted to the negative electrode. And so we call the negative electrode the cathode. Okay, so get those right in your head, that the anode is the positive electrode, the cathode is the negative electrode. So there are your key definitions. Make sure you learn those. And we've looked at why graphite is used for electrodes. Just then, the last point on the page is to look at that your most common electrolytes are molten ionic compounds. That just means ionic compounds that we've melted down into a liquid. Or we can also use aqueous ionic compounds. And you might be able to already think about, why does it need to be either in liquid form or in solution? We're going to look at that in the next page, but have a think, why do you think these electrolytes need to either be in liquid form or in solution? So aqueous, remember, means dissolved in water to form a solution. And we know from our year 11 studies that ionic compounds tend to be solids with very, very high melting points. And that's because there's strong attractions between the ions. And therefore a lot of energy has to be put in to break those bonds. So therefore ionic compounds are solids at room temperature. But we must either melt them down into a liquid or dissolve them in water to form a solution before electrolysis will even work. So it's something like sodium chloride, say for example. Sodium chloride would be a solid, so we need to either melt it down into a liquid or dissolve it in water so that it's a solution. So how does electrolysis work? And this is probably what you'll find the most confusing in this topic. So if you can get your head around this, then the rest of the topic will be much easier. If you need to play this part of the video a couple of times until you get it in your head, then please do. It's really, really important that you get this part, and it will honestly make the rest of the topic much easier. So we've already talked about the fact that electrolytes must be either molten or in solution. So it says here, this is why electrolytes must be molten or dissolved in solution. If you add that into your notes, they must be molten or dissolved in solution. Why is that? Well, if you remember back to year 11, when we looked at bonding and structures, we're talking here about ionic compounds. And this is something we talked about in year 11, particularly in our structures topic, which was unit 1.3. So electrolytes are ionic compounds. And if you look at the top of the page here, I have added in a picture that was in your year 11 notes of ionic compounds as a solid and then as a liquid. So as a solid, ionic compounds are held as a solid because they have strong attractions between their positive and negative ions. Remember, we talked about electrostatic attraction between the oppositely charged ions. So that's why they're a solid at room temperature, because there is strong attraction between the ions. But if we melt them down, then the ions are then free to move. So as a liquid, the ions are free to move. As a solid, the ions are in a fixed position within the lattice, and so they're not free to move. You can see that in your diagram with all the different bonds there that are shown. That means the ions are in a fixed position and so cannot move freely. Whereas when they are a liquid, they are free to move. And we talked about at the time how they can then conduct electricity because they're free to move and carry the charge. As a solid, ionic compounds cannot conduct electricity because they are in a fixed position within the lattice, and so are not free to move and carry charge. But as a liquid, the ions are free to move and carry charge. And that is sometimes asked in your exam. So it brings us back to year 11. It's relating year 11 content to year 12. In the exam, you're sometimes asked, why must electrolytes be molten or dissolved in a solution? And it's so that the ions are free to move and carry charge. Sometimes the question is asked in the context of, why do solid electrolytes not conduct electricity? So if they were a solid, why would electrolytes not conduct electricity as a solid? That's because the ions would be in a fixed position within the lattice, not free to move. So that will be asked in questions later on, and this is where you need to refer back to. that electrolysis must take place on an electrolyte that is molten or dissolved in solution so that it has free ions that can move and carry charge. If it was a solid, it would not conduct electricity as the ions would be in a fixed position within the lattice and so therefore not free to move and carry the charge. So think electrolysis needs a flow of electricity. Electricity will not flow through a solid electrolyte because the ions cannot move and carry the charge. So it needs to be a liquid or in a solution so that the ions are free to move and carry the charge and essentially conduct the electricity. And this next part can be a little bit tricky too. So let's make sure we get this clear in our heads. Negative ions, what are they called? They are called anions, A-N-I-O-N-S. Anions, which are negatively charged, are attracted to the positive electrode, which is called the anode. So think anions go to the anode. So if anions are negatively charged, they are attracted to the positively charged electrode, which is called the anode. So make sure that's clear in your head that anions are negative, the anode is positive. Why is that? Well, it's because oppositely charged ions attract. So make sure that that's really clear in your head. On the other hand, positive ions are called cations. So positive ions are called cations. That's the term we met in year 11. Cations, since they are positively charged, they are going to be attracted to the negative electrode, and that's called the cathode. So remember, cations go to the cathode. If cations are positively charged, then the cathode must be negatively charged. So sometimes it's easy to get those mixed up, so just ask yourself twice when you're doing these sorts of questions. Have I got this right? Because sometimes in an exam it can literally be a 1-mark question of name the negative electrode, and you would have to say that that's the cathode. But you're almost going through that process of, okay, if the negative electrode, then positively charged ions are going to be attracted to it. The positively charged ions are called cations, and so the negative electrode must be the cathode. So you just need to think twice about this. So remember, anions are negatively charged. They're attracted to the positive electrode called the anode. Cations are positively charged, and so they're attracted to the negative electrode called the cathode. So let's see what happens at each of these electrodes so that we understand what's happening during the process of electrolysis. So at the anode, first of all, let's ask ourselves, is that the positive electrode or the negative electrode? It's the positive electrode. Why? Because the negative ions, the anions, are attracted to it. So the first thing that you need to remember is that the anode is the positive electrode. So what happens at the anode? Well, at the anode, negatively charged ions, the anions, are attracted to it because opposite charges attract. So within your ionic compound, within your electrolyte, you will have positive and negative ions, and it's the negative ions that are attracted to the positively charged electrode, the anode. So the anions are attracted to the anode. So what happens to them? Well, what essentially we want is we want these ions to go back to their element form, in other words, with no charge. So we want these ions to lose their charge. And so what we are asking ourselves is, what do these ions need to do to get back to no overall charge? So why is an ion negative? Well, an ion becomes negative if it has gained electrons. Remember, electrons are negatively charged. Electrons each have a charge of -1. So if an atom has gained electrons, it has become negative, and that's what's happened to our anions. But essentially we want to go the other way around. We want our ions to become atoms again. And so what our anions need to do, our negatively charged ions need to do, is they need to get rid of the extra electrons that they have. If they have a 1- charge, then they'll need to lose 1 electron. If they have a 2- charge, they'll need to lose 2 electrons. So essentially they lose electrons so that they lose their overall charge and they become an atom. We want them to become an atom and lose their charge. At that point, the ions no longer have a charge, they have become atoms, and so they'll no longer be attracted to the anode, and so therefore they'll either sink to the bottom or they will bubble off if they are a gas, and we'll come back to that in our specific examples. So at the anode, the negatively charged ions, the anions, will be attracted to it. They will lose electrons to become atoms. So we wanted them to become atoms, and because they have an excess of electrons, we want those electrons to be lost. The next point in this box relates us back to the last topic that we just covered, our oxidation, reduction and redox. And it says here the loss of electrons is called, so if you remember the rhyme, oil rig. Oxidation is loss, reduction is gain. So the loss of electrons is called oxidation. And so at the anode we can say that oxidation takes place. So the key things here is that at the anode, the anions are attracted to it. They lose electrons to become atoms. Some of those atoms will combine to form diatomic molecules like chlorine and bromine and oxygen and so on. And it's important to remember that oxidation happens at the anode simply because you've got the loss of electrons. So that's at the anode. At the cathode, essentially the exact opposite happens. Let's remind ourselves first of all that the cathode is negatively charged. So the cathode is negative. So what will happen at the cathode? Well, again, remember that within our electrolyte we have positive and negative ions. What's going to be attracted to our cathode? It's going to be our positively charged ions, our cations, because opposite charges attract. So because the cathode is negatively charged, our positive ions are attracted to it. And we want them to become atoms as well. Again, we want these ions to lose their charge so that they become atoms again. So what needs to happen in terms of electrons? Well, remember, it's the opposite of what happens at the anode. If we want this to go back to an overall zero charge, it will need to gain negative charges. It will need to gain electrons. So we'll add that to a couple of our ions here. So at the cathode, these cations gain electrons to become atoms again. So they gain electrons to become atoms. What is the gain of electrons called? Well, the gain of electrons is defined as reduction. Remember, oxidation is loss, reduction is gain, oil rig. So reduction happens at the cathode. So at the cathode, it's negatively charged, so the positive ions are attracted to it. At the cathode, these positive ions gain electrons to become atoms, and so we call this part of the process reduction. So we've got oxidation happening at the anode and reduction happening at the cathode. So overall, electrolysis is a redox process because we've got oxidation happening at the anode while we've got reduction happening at the cathode. So we're going to be looking at some specific examples of some specific electrolytes and what they're broken down into, and what products we get and what observations we see. But it's really important that you understand what happens at each electrode, that you've got that the right way around in your head, that at the anode it's positively charged. So it's the anions that go to it. They lose electrons, and we call that oxidation. At the cathode, it's negatively charged, so the cations, the positive ions, are attracted to it. And they gain electrons to become atoms, and that process is called reduction. So make sure that you understand that. Rewind the video and go through it again if you need to, because it'll make the rest of the topic easier if you understand this. Over on the next page then you have your apparatus used for electrolysis, and this is kind of your lab scale apparatus. It's important that you learn this. This has been asked on an exam before and it was worth 5 marks. So make sure that you can draw this apparatus and that you can label it. So obviously key things in this is a battery first of all. Why do we need a battery? Because we need a flow of electricity through this. We need electricity flowing. So we might have a battery or we might have a power pack, for example. The lamp, it's not part of the electrolysis process as such. What do you think the lamp might be there for? Well, it's really there to ensure that we've got a complete circuit to prove to us that electricity is flowing through our circuit here. If the lamp is not lit, then we know that there's a break in the circuit somewhere. That could be because our electrolyte has become solid and therefore electricity won't flow through it. Or it could be because our source of electricity has depleted. So the lamp is there just to essentially ensure that electricity is flowing. Again, there have been questions in the past. For example, they've said if the electrolyte was solid, what would happen to the lamp, and you would say that the lamp would not switch on. Or they might ask at different stages of the electrolysis process what would happen to your lamp. So you're just thinking if electricity is flowing, then that lamp will turn on. If it's not, then it will be off. Conventionally the anode is drawn on the left hand side if you are looking at it. And then the cathode is drawn on the right as you look at it. Remember that your cathode is negatively charged because remember the cation are attracted to it, and your anode is positively charged because the anions are attracted to it. So make sure you can draw that. Maybe pause the video now and on the back of your booklet or in your blue book, try and draw out that apparatus because you could be asked that in the exam, and it would be worth a lot of marks if you were asked to do that. And as with any other apparatus diagram, you must label every piece of apparatus. A diagram without labels will lose you a lot of marks. So now we're going to move on and look at a couple of specific examples. The two specific examples that you need to know from your specification are the electrolysis of lead bromide and the electrolysis of lithium chloride. For each of these ionic compounds, you need to be able to write half equations, sometimes referred to as ionic equations, but they're really half equations for the reaction happening at the anode and for the reaction happening at the cathode in each examples. And you need to know the observations. So observations and half equations for the electrolysis of lead bromide and lithium chloride. Just a reminder, for half equations, we will be using electrons that are represented as E minus, the minus as a superscript up in the top right hand corner, and they each have a charge of -1, and we've done lots of practice of that in year 11, but also in our oxidation, reduction and redox topic as well, with writing half equations for that. So we're going to look at these two examples now. So first of all, we're going to look at the electrolysis of molten lead bromide, which has the formula PbBr2. What I would like you to do before you proceed with this video is to pause and to watch the YouTube video that I have attached in Google Classroom. This video really helpfully shows you that electrolysis reaction actually happening. It means you can actually visualize the observations rather than just learning them off. So please take the time to watch that. It's a really helpful video. You can watch the whole thing, but really the main focus is up to about 3 minutes and 45 seconds in, and that will be really helpful at explaining what is happening, explaining why it needs to be a liquid, and explaining the observations that you see. So pause the video now, watch that video, and then come back to this one. So hopefully you find that video helpful, and now we're just going to have a quick recap of those observations and make sure that we can write half equations for what is happening. And we're going to do this by taking each electrode in turn and discussing what happens at each electrode. So let's look at the anode first of all. So you must remember that the anode is positively charged. So the anode is our positive electrode. So what will be attracted to the anode? Well, we need to think about our formula first of all. The formula of lead bromide, we're told, is PbBr2. If you weren't given that in the exam, you might have to work that out, but it's worth learning the charges on the ions because lead is a bit of a funny one. Lead's in group 4, but it doesn't have a valency of 4. If you look in the back of your periodic table, you'll see that lead has a charge of 2+. So its valency is 2, Bromine is in group 7, so it has a valency of 1. So when you swap and drop those, you get PbBr2. So let's think about the ions that make up lead bromide, because remember that this is an ionic compound, so it's going to be made up of positive and negatively charged ions. If you remember from year 11, it's always our metal that is the positively charged ion and our non-metal that is the negatively charged ion. And that's because during ionic bonding, electrons are transferred from the metal to the non-metal. So the metal ion will always be positive, it's a cation. The non-metal will always be negative, it'll be the anion. And if you think about lead bromide, we've already discussed that lead ions have a charge of 2+, and the bromide ions, they have a charge of 1- because they are in group 7. But there will be 2 of those, because you can see our formula is PbBr2. So for every 1 lead ion, we have 2 bromide ions, and that's essentially to cancel out the charge. So what will be attracted to our anode? Well, because our anode is positive, it's going to be our negative ions that are attracted to it. So it's going to be our bromide ions that are attracted to the anode, and you can see that in the diagram. So the negative ions here are our bromide ions, and they have the formula Br-. Don't be confused by the 2 in the formula. That is just saying that we have 2 bromide ions. It's not that the formula is Br2-. So just be really careful about that. So what actually then happens at the anode? Well, we've discussed this already in a general term. At the anode, our negative ions lose electrons so that they can become atoms again. Remember, we want our ions to lose or gain electrons in order to become atoms again. In this case, they're negatively charged, so they're going to have to lose electrons. And they're losing electrons to lose that negative charge that they have and become overall no charge. So how do we write a half equation for this? Well, let's think about what we start with and what we end up with. What we essentially want to do is go from Br- to Br. How do we do that? Well, we need to lose 1 electron. Can you see how the bromide ion has a charge of -1? And so we need to lose 1 electron. How we show loss of electron is on the right hand side. If you're not so sure about that, just think about writing a half equation overall. To balance that half equation, I would need to put an electron on the right hand side because my left hand side is already negative. But what we know about bromine is that it is diatomic. Bromine exists as diatomic molecules, so it has the formula Br2. It can't exist just as a single atom. So I need to put a 2 here in my bromine. What does that mean about my bromide ions in this equation? Well, it means I'm going to need 2 of them because remember the atoms must be balanced. So I need to put a 2 in front of my bromide ion. And what does that mean about the number of electrons that are lost? Well, if 1 bromide ion loses 1 electron, I've got 2 here. So they're each going to lose 1 electron, and that will give me a total of 2 electrons. So that is your half equation. Make sure it's written exactly like that. 2 Br- arrow Br2 plus 2 electrons. Essentially what we've done there is we've written a half equation. To run you through that quickly again, essentially what we've got here is bromide ions forming bromine. But we know that bromine does not exist as single atoms, it exists as a diatomic molecule. And then you're going through your steps of writing a half equation. The first thing is to balance the atoms. I have 1 bromine atom on the left and 2 on the right. So I need to put a 2 in front of my bromine on the left. Then we add electrons to the side that needs to go down in charge. At the minute the charge on the left hand side is -2, on the right hand side is 0. So I need to add my electrons to the right hand side. But I've only added 1 electron there, so essentially the charge is -1 on the right hand side now. But I need a total of 2 minus and so I put a 2 in front of my electrons. That brings the charge on my right hand side down to -2. So half equations are a little tricky, but essentially you're thinking what needs to happen to this ion for it to become an atom. But where we have the likes of bromine or chlorine or oxygen, we need to remember that they're diatomic molecules. And so actually we need 2 of our bromide ions to make 1 molecule of bromine. That half equation is really important, and you need to be able to be confident in writing that half equation even if you're just learning it off. You also need to be familiar with your observations for what's happening at the anode specifically, and you saw this in the video. When you're thinking of observations, always think first of all, well, what am I making at this electrode? What am I making in this case at the anode? What is my product? So what is our product in this case? What are we making at the anode? We're making bromine. You can see that from our half equation above. So we are making bromine. So I then ask myself, well, what does bromine look like? What would bromine appear as if I was to make it? We learnt in year 11 that bromine is a red-brown liquid, but during electrolysis we have to keep this at a very high temperature to melt our lead bromide, because remember, lead bromide is an ionic compound, and we learnt last year that ionic lattices have a very high melting point because of the strong electrostatic attractions between your ions. So we have to put a lot of energy in to overcome that. So these electrolytes have a very high melting point, so we have to keep this reaction at a very, very high temperature to make sure that it stays as a liquid. And so at the high temperatures that we use in electrolysis, bromine is actually a gas, and you saw that in the video that you watched on YouTube, that rather than a liquid being formed, we form a gas. So yes, bromine at room temperature would be a liquid, but because of the high temperatures we're using, it is a gas. So we know that bromine is red-brown, so it's red-brown. You need to have both of those colours in. We also know that bromine is pungent, which means that it has a really bad smell. It would kind of choke the back of your throat. We also know that bromine is toxic. And as we've just discussed, at the high temperatures used in electrolysis, bromine is going to be a gas. And again, why is it a gas? Because of the high temperature. So why do we see these observations? It's because we're producing bromine. Bromine is red-brown, it's pungent, it's toxic. And in this case, it's in the gas form because of the high temperatures used. At room temperature, it would be liquid, but here we see that it's a gas. The fact that it's toxic, it means that we have to carry this out in a fume cupboard if we were to do it in the lab. So you may get asked a question, and there's questions at the end of this topic that ask you, why is this electrolysis carried out in a fume cupboard? And it's because bromine is a toxic gas. So you may want to add that to your notes, because that is a possible question. So in a fume cupboard, the exhaust gases will be taken away and will be treated before being released, so that you're not breathing them in. So you need to learn your half equation for what happens at the anode of the electrolysis of lead bromide. And again, you're thinking first of all, well, what am I producing? I'm producing bromine, and so you're writing a half equation for the production of bromine. And you're writing observations based on the fact that bromine is produced at the anode, and hopefully you should have seen that in the video as well. Let's now move on to what happens at the cathode. So first of all, we need to remember that the cathode is negatively charged, and that will determine what is attracted to it. So remember that our lead bromide is made up of positive Pb2+ lead ions and our negatively charged bromide ions, which we've already discussed, were attracted to the anode because the anode is positively charged. But we're looking now at the cathode, and so what we see is at the cathode our lead ions are attracted to it. So our cation here, attracted to our negative cathode, is our lead ions, Pb2+. Let's have a think about what needs to happen to them. So you can see them here at the cathode, and remember the goal is to get these back to atoms. So what do they need to do in terms of electrons to get back to an overall neutral charge? In other words, they don't have a charge. So they have a 2+ charge now. What do they need to do? Well, they need to actually gain 2 electrons. They need to gain 2 electrons to become overall neutral, to have an overall 0 charge. So at the cathode we see the gaining of electrons. This is reduction. So let's try and write this into a half equation. What we've got here is Pb2+, and then if you leave a little bit of space, and that is forming lead atoms Pb with no overall charge. How do we balance this? Well, we need to add electrons to one side of the equation. Which side needs to go down in charge? The left-hand side needs to go down in charge, because at the minute the left-hand side has a charge of +2 and the right-hand side has a charge of 0. So the left-hand side needs to go down, so we add our electrons to the left-hand side. How many do we need to bring it back down to 0? We need 2. So that cancels out your 2+ charge of your lead ions, and so your charge is overall 0. So that's your half equation. Pb2+ plus 2 electrons goes to Pb. And if you remember from our diagram, what we said was that our lead ions were gaining 2 electrons, and we can see that in our half equation here. Pb2+ are gaining, so plus 2 electrons, is giving us our Pb atoms with no overall charge. So that's our half equation. Here you can see that our electrons are on the left of the equation. So this is the gain of electrons, which we say is reduction. So that is explained in our half equation, and it's explained in the couple of sentences down below. Because our lead ion has a charge of 2+, it needs to gain 2 electrons to become overall neutral. What are our observations at the cathode? Well, again, just like with the anode, I need to think, well, what is my product? My product at the cathode is going to be lead. So what does lead look like? Well, lead is a metal, so it's going to be shiny grey. We're used to metals being a solid, and again, lead would be a solid at room temperature, but because of the high temperatures used, lead is actually a liquid at this temperature, at the temperature that we need to use for electrolysis. And you saw that in the video, how on first looks it looked like nothing was happening at the cathode, but when the solution, when the electrolyte was poured away, you could see that there was a bead of a shiny grey liquid at the bottom of the container that the electrolysis was done in, and that was our lead. So with electrolysis of an ionic compound, the observation at the cathode is always the same. You always see a bead of a shiny grey liquid metal, which sinks to the bottom. It sinks to the bottom because it's more dense than the electrolyte solution or the electrolyte liquid, and it's a liquid because of the high temperatures used. So the observations you would write in for what's happening at the cathode is that we see beads of shiny grey liquid metal formed, which sink to the bottom, and you only really see that when you pour the electrolyte away. So if you were asked for what could be observed at the cathode, you would say beads of shiny grey liquid metal formed, which sinks to the bottom. So there's a lot to learn there, but essentially the key things are that you know your half equation for the anode and for the cathode, and you know the observations for the anode and the cathode, but it helps if you understand what's happening as well. So we see with the cathode here that it's the metal ion that's attracted to the cathode, because the cathode is negative and the metal ions are positive. With the anode, we saw that the anode is positively charged, so it's the negative non-metal ions that are attracted to it. So you need to know those observations and half equations really well. What we're going to do now is look at one more example, the electrolysis of lithium chloride. So the next example we're going to look at is the electrolysis of lithium chloride. Lithium chloride has the formula LiCl, and that's because lithium is in group 1, so it has a valency of 1. And chlorine is in group 7, so it has a valency of 1. So swap and drop that, you just get LiCl. We need to think about the ions that make up lithium chloride. So lithium, because it's in group 1, will form an ion with a charge of +1, and we just write that formula as Li+. Chlorine, because it's in group 7, will form a chloride ion with a charge of -1 as well. But again, we just write the formula as Cl-. So our half equations will be a little bit easier here as well. So what we want to think about is what's happening at each of our electrodes. So remember, first of all, we'll look at the anode. The anode is positive, and so that means our anions will be attracted to the anode. Which is our anion in this case? Well, in this case, our anion are our chloride ions. They are negatively charged. So our anion in this case is our chloride ion. Let's try and write a half equation for what happens to our chloride ions. Well, remember what is going to be happening. We want our ion to become an atom. So we want it to lose its negative charge and become an atom. So it starts as Cl-, and we want it to form Cl. But we know that chlorine atoms don't exist on their own. They exist as a diatomic molecule. They exist as Cl2. So how many chloride ions will I need to form chlorine? I'll need 2 of them. But we need to balance this in terms of the charge. On the left-hand side, my half equation has a charge of -2. On the right-hand side, there's no charge. There's no positives or negative on the right-hand side. So the charge is 0. So I'm going to add my electrons to the right-hand side because that's the side that needs to go down in charge. But it needs to go down by 2, and so I need 2 electrons. Cross that 0 out because you can see the charge on the right-hand side is now -2 because of your 2 electrons. So there's your half equation written. So you can write it in terms of just the normal process of writing half equations, or you can also think about what's happening at the anode. So if I zoom in here, you can see my chloride ions attracted to the anode. And I'm asking myself, well, what do they need to do to get back to atoms? They need to lose an electron. So essentially they give an electron into the anode, and that will then be carried round in the circuit to the cathode where they'll be gained by the lithium ions, but we'll come back to that in a second. So essentially here your chloride ions are losing electrons to become chlorine atoms, but because chlorine is diatomic, I need 2 chloride ions, each of them losing 1 electron. So that's a total of 2 electrons lost. So again, at the anode, we see because the electrons are on the right-hand side, that's the loss of electrons. And the loss of electrons is oxidation. So oxidation always happens at the anode. Then what about our observations at the anode? Well, we have to think again, what is our product? So if you're ever asked for the observations at the anode or cathode of any of these electrolysis examples, think about what is your product. Always think, what is my product? In this case, my product is chlorine. What do I know about chlorine? Well, in year 11, I learned that it was yellow-green. You can refer to it as yellow-green or pale-green. I also know that, like bromine, it is pungent and it is toxic. And then what state is it going to be in? Well, chlorine is a gas at room temperature, and so certainly at the high temperatures that we're using, it's going to be a gas as well. So our observations are that a yellow-green pungent toxic gas has evolved. And we see those observations because chlorine is being made. And so you may see it as bubbles of yellow-green pungent toxic gas evolved. And again, similarly, if you were asked in an exam, why would this need to take place in a fume cupboard? It's because the gas produced is toxic. And so we don't want to be breathing it in. So at the anode, we have chlorine being formed. The chloride ions are attracted to the anode. They lose an electron to form a chlorine atom, and then 2 of those chlorine atoms bond together to form a diatomic molecule. You've got your half equation there, and your observations, again dependent on the fact that we have produced chlorine, is that a yellow-green pungent toxic gas is evolved. So let's have a think now about what happens at the cathode. So remember that the cathode is negatively charged. We'll draw that up here as well. So we need to have a think about our compound is lithium chloride. The ions that make it up are Li plus and Cl minus. So what is going to be attracted to our cathode? Well, we can see if we zoom in that it's the lithium ions that are attracted to the cathode. Why? Because they are positively charged and the cathode is negatively charged. Again, I need to think, what do those lithium ions need to do to get back to an atom, to get back to no overall charge? What do? They gain an electron. So they are going to take an electron in from the cathode. And if you remember back to our chloride ions, we said that they lost an electron. So they essentially give up an electron that goes into the anode as such. And then if you think about it, this will be connected by a wire connected to a battery or a power pack. And that wire will then go into the cathode. So those electrons flow all the way around our circuit and then are essentially picked up by our metal ions. So our metal ions are always attracted to the cathode. They will gain electrons to cancel out their positive charge and to become atoms. So let's have a look at our half equation. So our cation in question here is our lithium ion, Li plus. Our half equation, well, we start with Li plus. What does that need to do to become an atom? It needs to gain an electron. And where it's gain of electrons, the electron goes in the left-hand side of the equation. I think that is a wee bit easier to see than what happens at the anode, because that lithium ion needs to add on an electron to then become, and that's what our arrow means, a lithium atom, Li. Or you can write that as a half equation, thinking that you're going from Li plus to Li and then add an electron to the left hand side to balance it. And here we see, as we did with lead bromide, that the electrons are in the left hand side, and so this is the gain of electrons, which is reduction. So again, think oil rig, reduction is gain. So we can see from our half equation that the positive lithium ion is gaining one electron to form a lithium atom. When it becomes a lithium atom, it has no charge, so it's no longer attracted to the cathode, and so it will just sink to the bottom. And you may want to write that into your notes. So the reason why the chlorine gas escapes and why the lithium atoms then fall to the bottom of whatever container, whatever apparatus we're using for our electrolysis, is because once they have, for example, for the chloride ions, it'll be losing electrons. For the lithium ions, it'll be gaining electrons. Once they have done that, they no longer have a charge, and if they're not charged, they're not going to be attracted to the electrodes anymore, because we remember that the anode is positive, the cathode is negative, and the reason why the ions are attracted to them in the first place is because the ions have a charge and they're attracted to the oppositely charged electrode. But if we take, for example, our lithium ions here, once they gain an electron from the cathode, they form a lithium atom. That lithium atom has no charge, and so therefore it's not attracted to the cathode anymore, and so it sinks to the bottom. And that's why we see the observations that we do. So again, observations, you're always thinking, well, what is my product? My product this time is lithium, which is a metal. So what we see with the observations with this is that it's exactly the same as our lead bromide example. With lead bromide at the cathode, we saw that lead was formed, and we saw the observations is, where that a bead of shiny grey metal was formed, which sinks to the bottom, and that's exactly the same here. So if you could fill that into your notes, your observations at the cathode will be that you form a bead of shiny grey liquid metal. Don't say silver metal, because silver is a different metal, and that sinks to the bottom because it's more dense than the liquid electrolyte, and it's a liquid because of the high temperatures that we use. So our observations at the cathode we've just discussed, and our half equation is there as well. So you need to know these half equations for the anode and cathode, and the observations for the anode and cathode, for lead bromide and for lithium chloride. If there's anything you need to go over again, please do that now. But over on the next page, you have a summary of your half equations and observations for lead bromide and for lithium chloride. It's really, really important that you learn these because you can be asked for these specific half equations and these specific observations. They may ask you to write a half equation for a different example, so for the likes of sodium fluoride or potassium iodide, and you would follow the same format, but they tend to just stick to these two and the industrial example that we will look at in our next video. So just make sure you know these half equations and observations really well. There's a few things you should notice from comparing these two examples. So if we look first of all at our anode, the product at the anode is bromine for lead bromide and chlorine for lithium chloride. So what you should notice is that that's the non-metal. The half equation will also take a similar format. So once you've learnt one, it's just changing the symbol essentially. So you've got 2Br minus going to Br2 plus 2E minus. And you can see it's a very similar half equation for chlorine, just swapping the symbol. Okay, again, observations, there's similarities. With lead bromide, it's a red-brown pungent toxic gas. With lithium chloride, it's a yellow-green pungent toxic gas. So just learn the two different colours. Then you've got your cathode, and what you should notice is there's a similarity in your products at the cathode. You should see that it's the metal formed at the cathode in each case. Your half equation is similar, the only difference is that with lead, because it has a charge of 2+, then it needs to gain 2 electrons to become just a lead atom with no charge, whereas lithium only has a charge of +1, so it only needs to gain 1 electron. And then what you should notice is that the observations at your cathode for both examples are exactly the same, because you're forming a metal, and a lot of metals look very similar at these high temperatures. It's going to be a liquid metal, so they'll form this bead of a shiny grey metal. So learn those half equations and observations for those two specific examples really, really well, and making sure you can describe what's happening at each electrode as well, and that is very much dictated by your half equation, essentially just putting your half equation into words. So for example, with lithium at the cathode here, you would say at the cathode, lithium ions gain 1 electron to form lithium atoms. So it's putting that half equation into words essentially. And then finally for this video, I just want to talk you through quickly predicting the products of molten electrolysis. If you were to be given an example that wasn't lead bromide or lithium chloride. And again, it's about thinking about this twice, thinking about it carefully, and making sure you get it the right way round. What we have seen in our examples is that anions are always the non-metal. And so the non-metal is always formed at the same electrode. An anion is negatively charged, and so that always goes to the positive electrode, which is the anode. So what we're saying here is that at the anode, the product is always a non-metal. So because the anode is always positive, and because in an ionic compound, the negative ion is always the non-metal. We learned that back in year 11, because electrons are transferred from the metal to the non-metal. So the non-metal gains electrons essentially when they're bonding. So here the product is always going to be a non-metal at the anode, because the non-metal ion is the negative one, so it's attracted to the positive electrode, which is the anode. And then the opposite is true for the cathode, because the cation is always the metal ion. So if you think of an ionic compound, is always made up of a metal and a non-metal. The metal ion is always positive, and so it is attracted to the negative electrode, which is called the cathode. So in that sense, the product at the cathode is always a metal. So if you were given, for example, in your exam, if they said to you, what would be formed at the cathode for sodium chloride? You may think to yourself in the exam at first, well, sodium chloride wasn't one of my set examples. I learnt lead bromide and lithium chloride. But what we can see is the same thing happens each and every time. We know that our metal ion is always going to be positive, and our non-metal ion is always going to be negative. We're asked here, what is the product formed at the cathode? Well, the cathode is negatively charged, so it's going to attract the positive ions, which in this case are our sodium ions. So therefore the exam could ask you any example. At the cathode is always going to be the metal. At the anode is always going to be the non-metal, and that's something worth learning and making sure you have straight in your head and not get it mixed up. So, for example, we've got a table here that we want to fill out with what are the products at the anode and the cathode for each of these examples. So remember that your anode is positively charged, and so what does it attract? It attracts the negatively charged non-metal ion. The cathode is negatively charged, so it attracts the positively charged metal ions. So what is your product at the anode for magnesium chloride? Well, it's going to be the non-metal, so it will be chlorine. Make sure you don't write chloride. It's the chloride ions that are attracted to the anode, but when they have lost their electrons, they become chlorine. So chloride is used when it's a negative ion. When it's become the atom again, or the diatomic molecule, we call it chlorine. So it goes back to its original name. So don't call it chloride. You wouldn't get a mark for that. What's then formed at the cathode? Well, it's the metal that's formed at the cathode. So in this case, it would be magnesium. And we say it's the same thing each and every time. The non-metal is always formed at the anode. The metal is formed at the cathode. So what I'd like you to do is pause the video and try and fill out the rest of this table, and then play the video again just to check that you're correct. So pause the video now and try to fill in the rest of this table. So for aluminium oxide, what is your product at the anode going to be? Well, it will be our non-metal product, and so it's going to be oxygen. Oxide ions form oxygen. What is our cathode product going to be? Well, it's our metal in this case, which is aluminium. With potassium bromide, what's our product at the anode? It's going to be our non-metal, which is bromine. And at our cathode, we form our metal product, which in this case is potassium. And lastly then, with calcium chloride, what's formed at the anode? It's going to be chlorine, our non-metal. And then what's formed at the cathode? It's our metal product, which is calcium. So hopefully you can see from this that the exam could ask you any ionic compound, the electrolysis of any ionic compound, and you should be able to predict the products at the anode and the cathode of any ionic compound. Remembering that the anode will always be the non-metal, the cathode will always be the metal. We're going to skip past the extraction of aluminium for now and leave that for next week in our next video. But what I would like you to do now is to complete questions 1 to 5. Please complete them in your blue book or on file paper. Please don't just squish them in on your notes here. You'll need some space to write them out properly. Please put your full effort in. These probably won't take you too long at all, so try and get them right. If you're struggling with any of these, if you're not sure how to answer it, then please watch the different parts of the video again, because once you've got your head around this, these questions should actually be straightforward enough, and these questions always make up a significant amount of marks on the exam paper, so you need to make sure you understand it. And it's the sort of thing that can be tricky to get your head around at first, but once you've got it, hopefully it will stay with you and it will click. So if you need to watch any parts of this video again, then please do. So first question is very straightforward, just your definitions, and make sure those are your key definitions from the first couple of pages of your booklet. Number 2 is just predicting products like we have the last part of this video. Question 3, write balanced half equations to show what happens at the electrodes. I want you to write one for the anode and the cathode for each. So for lithium chloride, you will have a half equation for the anode and a half equation for the cathode. Again, with lead bromide, you will have a half equation for the anode and a half equation for the cathode. So essentially, you will have 4 half equations overall for question 3. Question 4 and 5, and they are then over the page and should be straightforward enough. Again, you can answer each of these questions from your notes. You shouldn't need to do any other research. So if you're not sure about a question, look carefully within your notes and find your answer.